Hello everyone, my name is Higuma. I'm a master course student from the University of Tokyo Sezaki Laboratory. Today, I'm glad to introduce our research, which is called Towards Estimating UV Light Intensity using GPS Signal Strength. First, I'm going to give you an excerpt of the results. The ultimate goal of the research is estimating UV light intensity from a smartphone GPS signal strength. This time, we conducted an experiment as a means to realize it. As a result of the obtained, under certain conditions, the correlation higher than 0.87 was observed between UV and signal strength, and similar trends were shown whether the phone was placed on the ground or in a pocket. Background. Due to the progress of urbanization and changing lifestyles such as Uber Eats, Netflix, and Amazon Hub, many people have been spending more time indoors, hence they tend to receive less direct sunlight than ever before. For example, a research conducted by the National Trust showed that the present generation of children play outside for an average of just over 4 hours a week. This compares unfavorably with an average of 8.2 hours for their parents when they were children. This situation is spurred by COVID-19 infections such as staying at home. Not being exposed to direct sunlight means not being exposed to UV. Although excessive UV exposure increases the likelihood of developing skin cancer and wrinkles, moderate UV exposure is necessary to produce BD in the body. Deficiency of BD linked to hypocalcemia, bone softening, and depression. So, adequate BD intake is important. However, natural foods that contain BD are limited. Therefore, BD production in the body due to UV exposure is recommended. Here's an overview of research. As mentioned in the background, BD production in the body due to UV exposure is recommended, but both excessive and inadequate UV exposure is harmful and needs to be monitored. But then, there's a problem. Although it is possible to carry a UV sensor to measure UV light intensity, the burden on the user is high. It would be nice to have a more accessible tool to measure it. Therefore, we study the estimation of UV by using the GPS module of the smartphone. The reason why we use smartphone is most developed countries have at least 90% of the population that use mobile phones, like this figure. And nearly all of those devices have a GPS module, and we would like to determine the UV exposure using the GPS module. Before we get to the related work, let me explain the UV. UV radiation is divided into UVA, B, and C, depending on the wavelengths. UVC has serious effects on human health, but it is shortest wavelength in the three types, and thus UVC cannot reach the ground. UVA B can be measured on the ground level. Excessive exposure to UVA B increases the risk of disorder such as skin cancer, while moderate exposure to UVB is necessary for the production of BD in the body. In short, UVA have a negative effect, and UVB have both positive and negative effect on the human body. Therefore, monitoring of UVA and UVB is important. In addition, the UV index is an index of the effects of UVA-B on the human body. Therefore, monitoring the UV index is also important. UV index is global indicators, and the higher the value, the greater the impact on the human body. Some research is done to estimate the amount of UV light produced by BD. Mioj and others estimated the time required for sunbathing if the body is able to produce a daily recommended level of BD during this activity, 5.5 microgram per day for adults. If we know the UV index, we can estimate the sunlight exposure time required for the production of BD. On the other hand, some research of state estimation using GPS signal strength. GPS signal strength has been used to detect volcanic problems, measure soil moisture, investigate the relationship between the energy consumption of a localization application and GPS signal strength. However, there is limitation in both research. In their research, the UV index itself is measured using a UV sensor. Therefore, each user has to carry a UV sensor every day. To the best of our knowledge, GPS signal strength has not been used to estimate UV values. Other than the related research, if we can estimate the amount of UV radiation using the radio wavelengths of the smartphone, the aforementioned problem can be overcome. In addition, if we can automatically estimate the UV values that the user is exposed to or is being exposed to with their mobile device, the above applications will be possible, such as reminder of the required amount of UV, notice of indoor evacuation, long-term record of UV exposure. As an experimental study, we measured UV values, including UVA, B, and index, and GPS signal strength, at different places and situations. Finally, based on the measured values, we analyze the relationship between these values for estimating the UV light intensity. As a UV sensor, we use BEML609 R75 that can measure UVA and B and index simultaneously. As shown in figure, that sensor is connected to an M5 stack, which is an ESP32 base module. The sensor data are collected via I2C and stored in a micro SD card in a CSV format. This module starts to measure UV values every second after synchronizing the time using network time protocol. We use GNSS logger to correct the signal strength values. This is an application for correcting low GPS signal, including signal strength data. The corrected data can be exported as a text file. We install the application on a Google Pixel 3a Android 10 smartphone. The smartphone has a module for receiving GPS signals from 5 types of positioning satellites: GPS, GLONASS, Beidou, Galileo, and QZSS. These are the measurement locations: under a motorway, at a bank, beside an apartment, beside a house, indoors. We took measurements at each location in the sun and in the shade. Measuring equipment is installed in the area surrounded by the red dotted line. Measurement procedure. We measure UV values, signal strength at 10 places as shown before, into smartphone situations on the ground and in the pocket. In the pocket situation represents measuring the UV values and the signal strength with a phone in the pocket and is intended to be used in a realistic situation. The measurements are performed as follows. Set the UV sensor on the ground at each place. Set the phone at each situation, on the ground or in the pocket. Measure UV values and signal strength for duration of 3 minutes. Move to next place. Here's characteristics of each parameter in the collected data. From the result wedge t-test, significant difference was observed between outdoor and indoor values in UVA, B index, and signal strength. In addition, the values of UVA, B index indicate a significant difference between in the sun and shade case. The signal strength value does not indicate a significant difference between the sun and shade case outdoors. However, the median values of the sun case were observed to be larger than those in the shadow case. Here's correlation between UV values and signal strength. The top and bottom graphs are plots of the same data. These figures show the correlation between UV values and signal strength. Round marks are for the sun, and X marks are for the shade cases. When the measurement data of all places are incorporated into one dataset, the correlation between signal strength and UVA is 0.52. Signal strength and UVB is 0.68. Signal strength and UV index is 0.61. Bottom figure shows the correlation when the collected data are divided by the sun shade cases. In the sun case, the correlation between signal strength and UVA B index was higher than 0.90. In the shade case, the correlation between signal strength and UVA B index was higher than 0.87. Divided by the sun and shade cases, the correlation is higher. This is in the pocket situation. The same trend was seen when smartphone put in the pocket. Discussion. Significant correlation between UV values and signal strength was observed even if a smartphone was in the pocket. This result indicates that UV values can be estimated to a certain extent using signal strength collected from a smartphone. But there are tasks. Signal strength data was collected in a very ideal environment, stationary on the ground for 3 minutes. In real space, users own their phones at various locations and move frequently. The impact of those factors is also not clear in this study. UV and signal strength values vary with various environmental variables. We do not take into account any differences in the number of satellite positions, angles, or types. And measurements and evaluation experiments are needed in more environments with different weather conditions, time of day, seasons, etc. Experiment was conducted at some time of the day. In order to address these elements, a combination of UV and UV for the entire baseline region is needed. If these problems can be overcome and the information of sunshade can be detected, it will be possible to estimate UV values with high accuracy. Conclusion. In this study, data were measured and analyzed in an ideal environment as an initial stage for the study. However, the data in this paper are not sufficient to predict UV values in a flexible manner in response to factors such as location, time of day, season, and weather. And it is necessary to address these factors in the future. As future work, we will take into account the above things and 3D maps. Thank you for your attention.